So for this lesson, we're going to talk about the fundamental concepts of OOP. In the previous video, we talked about the paradigm itself and what is its philosophy. And we sort of had a little bit of introduction on what these fundamental concepts are. In this video, we're going to talk about them in detail. The first one is encapsulation. One of the most important design principle of object-oriented programming is the concept called encapsulation. And I've said this again and again, and I don't mind saying it right now, that OOP's innovation that made the paradigm a solution to the issues of state is its mechanism to construct boundaries wherever you want. And you should want to put it in between irrelevant data. This mechanism right here is what you also call encapsulation. And here are a few important points to remember. Encapsulation, when done correctly, makes your system approach a more accurate simulation of the real world. The more you encapsulate related data and methods, the more you'll create cohesive classes that have definite and indivisible purpose. When you do this, you're able to subdivide all of the related behavior and data down to small enough chunks to the point where this specific mechanism right here cannot be divided anymore. This is its sole responsibility, and you can combine this specific mechanism with other mechanisms to create more complex mechanisms, for example. And this concept of encapsulation is not only true for object-oriented programming, this specific point right here. In fact, the same thing is done in other paradigms like functional programming, which aims to create purer, smaller functions that will then be combined to more complicated, that will then be composed to create more complicated mechanisms as well. In the context of OOP, encapsulation, when you do it correctly, you do it by encapsulating objects as deep as you can. The second point, you should encapsulate what varies. And this adage right here is, one of the most repeated phrases in object-oriented programming, encapsulate what varies. What this means is that things that always change should be encapsulated deep into the structure of your code. This will help you with maintainability since changing isolated data or behavior will have less impact to the whole system. The more you encapsulate something, the more you isolate this specific data or behavior from other parts of your code. By encapsulating your data deeper and deeper, anything that you change about that specific data or behavior will have less and less of an effect to the whole system itself. To illustrate this example right here, if you ever consider a system that calculates tax, for example, by multiplying amounts with some tax rate, which one do you think is the best implementation for tax calculation? So the first one right here is the global variable called tax rate. Second is to hard code the tax value for every instance of use. So for example, if ever you want to calculate the tax for the specific income of this specific instance, you have a multiplication operation right there with the literal value of the tax rate, for example. Let's say the tax rate is 0.1%. So there you go. And what about implementing some function called calculate tax, which calculates tax? So these three different cases are three different levels of encapsulation. And you can sort of guess which one of these three have an effect. And you can sort of eliminate which ones you know as bad practice. For example, hard coding the tax value for every instance of use. This is no level of encapsulation at all, where this specific behavior, or in this case, specific data, which is tax rate, for example, 0.01, which has a distinct chance of changing since taxation and relevant calculations like these are subject to loss. So, for example, if the law has been changed or there's been some additions or whatever, then you have to change that tax rate to something else. And if you do choose to do the second way where you hard code the tax value for every instance of use, since you haven't encapsulated this specific data at all, then you would have to change it for all instances of use as well. So the second level of encapsulation would be the first one, which is a global variable called tax rate. If you do implement it this way, then if ever there is a change for the tax rate, then all you have to do is to change the definition of tax rate. So if tax rate is a global variable stored somewhere accessible to all of the systems uh, that will access this tax rate variable, then all you have to do is to change this into something else, and it will affect all instances of use. But the problem with this one though is, first, you might think that a global variable is not really good practice. And even if you implement some safeguards that disallow the mismanagement or the careless changing of this tax rate variable right here, uh, this will still have an impact on mutation and side effects. This specific uh, this specific way of encapsulating is better than the previous one, but it has still issues. An issue that could come up, for example, is that you're assuming that the tax rate will be calculated by directly multiplying the tax rate with some amount of money, for example. So let's say, since this is what you're used to, then all you have to do for your tax calculation is something similar to a tax rate times some amount of money. What if there were changes on how the taxation is calculated? For example, you add some flat amount, for example, some constant amount. And what if that constant amount changes as well? Then you would still end up changing your hard coded, or not really hard coded, your tax rate multiplications, since you have to add this extra addition right here. Now, of these three, the deepest level of encapsulation that you can do is to create this function called calculate tax, which will take care of calculations of taxes no matter what that calculation of tax is. And at the same time, by creating this deep level of encapsulation, which is calculate tax, you will also have created uh, a good level of abstraction between the actual behavior calculate tax and what it actually does. Because anytime that you need to calculate tax for a specific amount of money, all you have to do is to call calculate tax. You don't even have to concern yourself about the actual implementation of what the tax calculation is. You don't even have to care about that, since you just have to use this deeply encapsulated, pretty abstract method called calculate tax. Encapsulating what varies helps with the maintainability, since changing an isolated data or behavior will have less effect to your whole system. And encapsulation means both attributes and behaviors. This is the third point. Concrete objects should be given the responsibility of implementing their own behavior. So when you're encapsulating, you're not only encapsulating the attributes or the form of your classes, you're also encapsulating the methods or the behavior of that object. Sometimes people forget this part, that this is also uh, something that you can encapsulate as well. So the next pillar, or the next design concept of object-oriented programming, is the concept called inheritance. So we will discuss inheritance a little bit deeper, Pajid, in the future lesson about class relationships. But this is a little bit of introduction on what inheritance means. Inheritance is the concept in which the definition of a class is derived from another class. An existing class, for example, a superclass, which has a lot of names actually. It is also called a base class, a parent class. And in this course, we also call them generalizations as well. These existing classes passes all of its visible attributes and methods to a subclass, also called derived class, child class, specializations. Inheritance allow for these passing of related or visible attributes, and this is the reason why this concept is called inheritance, in the same way where your parent or your grandparent, for example, passes something down to its successors, to its descendants. And that's where the parent and child class terminology also comes from, because parents or children inherit something from their parent. The concept of inheritance is also a representation of the real world. Sorry, that's repeated. You use inheritance to represent generalizations and specializations. A superclass is again what you call a generalization of a subclass, and a subclass is a specialization of a superclass. In this presentation, I actually have a concrete representation of inheritance, but I actually have a better example for that in the future lesson, so we can actually skip this for now. The next uh, important design concept of object-oriented programming is the concept called polymorphism, and it's actually a bit related to inheritance. If you try to dissect the meaning of the word polymorphism, polymorphism literally means multiple forms, poly and morph. One of the core philosophies of object-oriented programming allows object instances to exist in multiple forms. What this means code-wise is that types of object instances can be decided during runtime. So this is a reference to the example that I will skip for now. There's also another type of polymorphism that is not necessarily shared by all OOP languages, and this is what you call compile time polymorphism. Because polymorphism is also another terminology in object-oriented programming or programming in general that is a bit overloaded. So compile time polymorphism is the specific type of polymorphism where functions, the feature where multiple functions can have the same name as long as they have different parameter type signatures. This is also known as method overloading. So you can find this specific feature on OOP languages like Java, C++, and etc., and their derivatives. Other OOP languages do not have this feature right here, such as Python, for example. But this is not really the important polymorphism concept about object-oriented programming. The important one is what we call runtime polymorphism. Runtime polymorphism is basically achieved using specialization and realization relationships between objects. We will discuss more about these two right here, these two relationships during class relationships. And these two relationships enable the concept of polymorphism to exist in object-oriented programming. So for example, let me just refer the previous example that I used right here. So an object instantiated to be of type primate is also an instance of an animal because a primate is just another specialization of an animal. We will actually discuss this using the examples that I used in class relationships. So realization and specialization relationships like book, borrowable item, primate, and animal, for example. So these realization and specialization relationships guarantee that you can interact with a subtype as its supertype, and you can interact with concrete classes with its abstractions as well. And that's all for this short presentation.